All right, everyone. So let's look at the solution of this problem. An Olympic athlete jumps from the ground at the speed of 10 meters per second at an angle of 15 degrees above the horizontal. How high does the athlete jump? How long does the athlete stay in the air? And how far does the athlete land from its starting position? So this is projectile problem. So we can assume that the acceleration is only due to gravity. So we can kind of like do a rough sketch. So if we assume that athlete is a particle like this, so the athlete jumps with speed of 10 meters per second. This is initial speed at an angle of 15 degrees. And then we can imagine that this will be a trajectory that's going to follow something like this and then going to hit the ground at some point, let's say point C. So usually I take this to be point A, which is the starting, the launch position. Highest position, the maximum height, generally, let's call this B. And then the final position, which is C, will be where the athlete lands. It's a good idea to write down all the given information. Let's make a table where we're going to write what's given to us in the problem. So we're given the initial velocity, which is 10 meters per second. We're given the initial launch angle, which is 15 degrees. And we're given that this is a projectile problem, right? If somebody jumps or you drop something, you throw something, that's pretty much a projectile problem. Remember, projectile is nothing but a two-dimensional free fall. Okay. So that means indirectly we're given that there is no horizontal acceleration and there is a vertical acceleration of negative g, where g is the acceleration of gravity with a magnitude of 9.8 meter per second square. And then if you look at the direction, it's also given in terms of y-hat direction. Now, what we want to find, obviously we have three-part problem. In part A, we want to find maximum height. So pretty much position of B, which is we're going to define as maximum height. For part B, we're going to find total time. So T total. So those are the unknown variables. And then for part C, we want to know basically the range, right? What is then the delta X, right? Or you can take like, let's say the X of C. So this is the unknown. So in a way, this will be then delta X, which is sometimes is also known as range. And obviously for part B, we want to find the delta Y between points A and B. And that will be basically this position right here. So to start with, let me write down all the equation that we have for the free fall. But this is projectile, which is two-dimensional free fall. That means we have to take both X and Y coordinate system into account. So remember, in the X direction, we have no acceleration. So no acceleration, which means AX equals 0. This implies that velocity in the X direction is constant, which means at any given time, for example, initial horizontal velocity, final horizontal velocity, or velocity at any given time is exactly the same. So it's constant. And generally, we have just one equation then to represent the type of motion where there is no acceleration and constant velocity. Remember, this means this is a uniform motion. So for this equation for range, delta x is then equals to then Vx times time. So I don't need to write down initial x or final x because all the velocity in x directions, right, they're all exactly the same. Now, there's also another equation for horizontal displacement, which is range. And this equation, let me write down the R is sometimes the notation that we use for the range. So if R is delta x, you can also calculate this, which is generally assumed to be time-independent equation. This will be initial velocity square times sine of 2 theta, which is the launch angle, divided by g. So this is another equation that we technically can use for the range. Okay, so This is in the x direction, and let's look at in the y direction. Well, in the y direction, remember we have a vertical acceleration equals negative gy hat, which means negative 9.8 meter per second square, which means we have then change in motion in the y direction. So, and since acceleration is constant, we technically allowed to use those kinematic equations. So the kinematic equations are, if you remember, initial velocity in the y direction. We're going to include all the vertical subscripts to, to indicate this is only allowed to be used in a vertical direction. So this is the final velocity in the y direction equals initial velocity in the y direction. Generally would be then plus acceleration times time, but acceleration equals negative g, so I'm just going to put negative g times time. This is free fall specific kinematic equations. Equation 2, y final equals y initial plus initial velocity in the y direction times time plus 1/2 at squared. Again, a is this, substituted by negative g, so minus 1/2 gt squared. Equation 3, final velocity in the y direction square equals initial velocity in the y direction square minus 2 times g times the delta y. And then the fourth equation will be delta y equals initial velocity in the y direction plus final velocity in the y direction divided by 2 and the quantity times time. All right, so we have this 4 equation that we can use in a y direction. And so technically 2 equations, right? We can use then for the x direction. So generally just one equation, the other one just a different version of that equation pretty much. Now, in terms of then what we have based on what we're given and what we want to find for part A, if you go back and look at part A, it says how high does the athlete jump? That means we want to know what will be the displacement in a y direction only when the object goes from point A to point B. Remember, point B is then our maximum height. So if we look at then that particular motion, which we can kind of, squeeze in right here, that means we want to go from point A to point B. Now, to remember what you want to do always with the projectile problem, if you're given initial velocity and the launch angle, is to calculate the components of your initial velocity. So that means you want to calculate initial velocity in the x direction, which will be v naught cosine theta naught, and initial velocity in the y direction. Initial velocity in x direction and y direction. Basically, all you need for those is the initial velocity and the initial launch angle, and those are the things we're given. That means initial velocity in the x direction will be 10 meter per second times cosine 15 degrees. Okay, if we do these calculations, then we should be getting 9.6 meter per second. Well, actually, I can probably write this as 9.7 because it's 9.66. And if I solve for the vertical velocity in a y direction initial, this will be then 10 meters per second times sine of 15 degrees. Again, if you are confused about why I have those components written like that, remember, right? If I take the initial velocity and if I break it down, the initial velocity component in x direction will be this particular vector, which will be then if I, you can see, right? If I take this to be y-axis, if I take this to be the x-axis, then that's the projection in the x direction. And this will be then the projection in the y-axis, right? And if I move this here, the y component is then the opposite to that angle theta, and x component is the adjacent to that angle theta, which means that x component will be in terms of cosine and y component will be in terms of sine. All right, so if I calculate this, I should be able to get 2.6 meters per second. All right, so now I need to calculate those initial velocities because you can see, right, if I look at these equations right here for the y direction, I don't have initial velocity or the launch angle. All of those are given in terms of component, right? So, v initial y, v final y, and y final. That means, I need to find these two if I can. This will be the first step. And then you can write this v initial in the y direction can be used right there, can be used right here, can be used right there. That means all of those equations basically going to be using that particular quantity. All right, so to get the maximum height, we can see that based on what I'm given initial velocity at point A. And remember, right, this will be then initial velocity in a y direction at point A, which is then 2.6 meter per second. One thing then to remember is that whenever the object goes to the maximum height, remember the blue vector here will be then the velocity vector itself. It's always tangent to the trajectory. At point B, velocity vector will be like this. So this is the velocity vector itself at point B. As you can see right there, it has no vertical component. At this point, velocity in vertical direction, velocity in a vertical direction at point B is equals to 0. And velocity itself is it's going to be equals to its x component. That means the velocity at point B actually is 9.7 meter per second. It has no y component. It's very similar to when you throw objects straight up. It goes, it reaches the maximum height, it stops, then comes back down. So you can think of like instantaneously at that point B, or that instant of time, in a y direction, it kind of stops because after that, the trajectory of the velocity will be down, so the direction of the vertical velocity then changes. Where before that, it was up. All right, which means if I'm going from A to B, velocity at point B in a y direction is 0. So which is going to be my final velocity. So my initial velocity is 2.6. My final velocity in a y direction then going to be 0. And since I have also acceleration, I can then combine them together with, initial velocity, final velocity, acceleration, and use equation 3 because I don't have any, I'm not given the time, but equation 3 is time independent. I can use that equation to solve for delta y, which will be the displacement between points A and B. All right. So velocity at B square equals velocity at A square minus 2g delta y. So this is 0. Velocity at point B, right? As we said, this is vertical, right? It is 0. So then velocity at A in a y direction square minus 2g delta y. Rearranging this, move this term to the left. So it becomes 2g delta y equals initial velocity in a y direction square. And then divide both sides by 2g. So delta y equals initial velocity squared divided by 2g. So this will be then 2.6 meter per second. Remember, we're using this quantity, right? Because that's the velocity in a y direction component. Square divided by 2 times 9.8 meter per second square. So then delta y, let's write down here. The delta y, if we calculate that, it should be then 0.34 meters. There. So this will be the answer for part A. So we have now delta y. That means this is, we can just do a rough sketch again. This is initial velocity, initial Lagrange angle. So this is point A. Is when it goes to point B. So position of B then is 0.34 meters compared to position of A, which we can take that to be 0, which is our ground, right? Our reference position. Obviously, it's going to then also continue and then hit the ground at some point C. So then Y of C, which since again, it's the ground, we can also put that as 0. Part B is asking what will be then the total time, right? So how long does it stay in the air? That means we want to know the time to go from A to C. That means this is what we call total time. Now, there are a couple of ways we can solve this part, right? And I'm going to show you both ways right now. So the first one will be to just directly go from A to C. And we can see, right? I'm given vertical position of A, which is 0, which is going to be our initial position. I'm given vertical position of C, which is going to be our Y final. And we know that we start from, let's say, t equals 0, right? We start at point A, and we can take that to be our starting position. So it's 0. We have the velocity at that point, right? That means, we have v naught y, which is 2.6 meter per second. We have acceleration equals negative g. Position of A equals 0, which is my initial position. Position final, which is position C, also 0. And then I want to find time. Obviously, I'm not given final. I don't know how fast it's moving at this point, right? I don't know. Like, let's say in a y direction. I don't have that information at this point, right? So, like, let's say I'm not given that directly. So, but I don't really need that because there was one equation that was time independent and also, sorry, final velocity independent and allows us to solve for the time. And that equation is number 2 over here. So number 2 allows me to solve for the time even if I'm not given the final velocity. So that means we come back here and say, all right, so y final equals y initial plus initial velocity in the y direction times time minus 1/2 gt squared. That's the equation 2. Now, the good thing here is this is 0, this is 0. That means our displacement is 0. Then plus v naught t minus 1/2 gt squared. I take this term, move it to the left. So it becomes 1/2 gt squared. It was negative on the right side, becomes positive on the left side, equals v naught t. Now, the good thing about having, let's say, starting from the ground and hitting the ground, that this second equation ends up giving us a simple, let's say, calculation. Because at this point, because my displacement between points A and C in a vertical direction equals 0, I don't have a component there. So this is 0, which allows me then to cancel the time over here. If, for example, it would land on top of something, right? Maybe like, let's say y of c is any different than, let's say, a, then it would be a quadratic equation. Let's say if it would land like on top of the roof or something like that, then this would have been, obviously y final would not have been 0 anymore, and this would have been then a quadratic equation, which is, again, nothing complicated, but obviously it had to require us to make a few extra, steps to do the calculation. But here I cancel the time because, we don't have anything like that, right? So the object actually lands to the ground. So canceling t on the right side and one of the t's on the left side because it's t squared, I end up with 1/2 gt equals v naught y. And then, multiply both sides by 2, then divide both sides by g, allows me to get rid of everything but time on the left side. And time equals 2 times initial velocity in the y direction divided by g. So 2 times 2.6 meter per second divided by 9.8 meter per second square. So I can then calculate the time. So the total time here will be 0.53 seconds. There you go. So this will be then one of the ways we can solve this problem. The second method would be to find how long it takes to go from A to B. That means basically find this particular time, the time from A to B. Now, the interesting about this is that because we start from the ground and we go and hit the ground, we can see that we have exactly same displacement from A to B and B to C, which means one of the things we can do here is we can simply solve how long it takes to go to the max height. Now that even we have the displacement, but even without displacement, it's a very easy calculation. And then we can say that the time to go from A to B is the same as time from B to C, which means the total time is just 2 times the time to the maximum height, which is from A to B. And then we can then just double that and get the same answer. Because going from A to B, it's rather a simple way, for us to solve for the time. Because we have the initial velocity at point A, and that's 2.6 meter per second in a y direction, remember. We have acceleration equals negative g, and then we know that final velocity at point B equals 0. We know that because that's our maximum height. So using equation 1, v final y equals v initial y minus gt, then I can say this is 0, and then rearrange and so forth, move the gt to the other side. So gt is equals to v naught y. Then divide both sides by g. So v naught y over g. So this will be then 2.6 meter per second divided by 9.8. And the time we're going to get here will be equals to 0.26. with something. So 0.26, let's say 3 or something like that seconds. And then you can write this will be then t to the maximum height, and the total time will be 2 times time of the maximum height. So double that roughly gives you this, right? So approximately 0.53 seconds. There you go. So there are a couple of ways we can do that. Now, remember this, right? So this work, that means I can do this because my object started from point A, reached the maximum height, point B, then came back, and final position is on the same vertical height as the A. That means I have same A and C, which means that the distance from A to B is exactly same as distance from B to C. Okay. If that was not the case, I would not be able to double the time to the maximum height. Again, imagine if there was a roof there or something like that, and it landed on, you can see, right? Going from A to B is significantly longer than from B to C, which would have been this point right there. So you can't double it anymore. So you have to find the other way to solve for the time, which would have been like, let's say, if you have position of A and position of C, you can still use equation 2, but just becomes a quadratic equation. It just, this method would not have been, you would not be able to do that second, double the time maximum height to find the total time. All right, so the final part C, then it's asking for a range. Okay, so now at this point, we have already a lot of information. That means we not only have the initial velocity in the x direction, that was 9.7 meters per second. We know that there is no acceleration in x direction. We also know that the time, total time, is equals to 0.53 seconds. Remember, the time is universal. That means it's both for x and y directions. And one equation we had for the range, which was the delta x, was just Vx times time. And obviously, this is the total time. So that means it's 9.7 meter per second times 0.53 seconds. Then we can calculate the range just simply using that equation. So this would give us 5.1 meters. There you go. Now, there is another method to solve for the range. And this one is, you have to be careful with this equation. This one only works. So that means we're done with this. Let's say this equation then only works if y of A is equals to y of C. Again, that means your initial vertical position is the same as your final vertical position. That means you start from the ground and come back to the ground. For that, there's this equation for range, which is, r and or delta x. So this is v naught square times sine of 2 theta divided by g. So this equation is more or less, it's like combining equation 2 and equation in a x direction for this range, but just, eliminating time. Okay. So this equation pretty much will give us a range, even if you don't have the total time. So this will be then, this is not component, this is V naught itself, so it becomes 10 meters per second times sine of 2 theta, that means 2 times 15 degrees, divided by 9.8. If we do the calculation, we should get exactly same 5.1 meters as we did above. All right, so this would have been then a couple of different ways of solving this particular part as well.